So I will talk about scale winds for real-time support to mesoscale forecasting. I'm Ed Stoffelen from KNMI. I lead an active remote sensing group here at KNMI. And my group is working on spectrometer winds from all different international satellites. We do it on behalf of EUMETSAT in the Ocean and Sea Ice Satellite Application Facility. And we are also part of the services, and we deliver software to the EUMETSAT Numerical Weather Prediction Satellite Application Facility. So we provide both the software and the data from wind spectrometers. I'll start with the introduction and then talk about the spectrometer winds, model winds. Model winds for forecasters are of course quite important for advisories. So the talk is mainly about how spectrometer winds can provide new information that has been just observed and help you to advise in your advisories, which are of course based on forecasts often, and then talk about the mesoscale forecasting part at the end. So if you look at the statistic of where events happen across the world, and then you see that many events happen actually close to the coasts. Many events are either meteorological events or hydrological events, but also climatological events. So this is statistics from 2012 to 2017. And you see all these different events, and I also provide here a statistic from 2017 about how many people were affected, how many were killed, and how enormous the costs are of these events. The increase of the cost is of course on one hand related to climate change perhaps, but certainly it's related to more infrastructure that is being built, so it's certainly related to the further development of the world. And also the associated losses when something unexpected is happening. Fortunately, weather forecasts keep improving to forecast such weather events. So here you see a plot where in the vertical you see the scale of, in this case, the ECMWF model in percent. So 100% forecast would be perfect. There's two lines in each color, an upper line which is the skill in the northern hemisphere and a lower line which is a skill in the southern hemisphere. And you see here a timeline from 1981 to 2017. And the blue color is for a 3-day forecast, the red is for a 5-day forecast, the green for a 7-day forecast, and the yellow is for a 10-day forecast. And you see that all these forecast skills are actually increasing in time with roughly the same pace. And this is just to indicate that the skill of these forecasts actually depends on the amount of information that's in the initial state of the forecast. So that means that we want to get a very good initial state in order to be able to make good weather forecasts. You also see that around the year 2000, the skill in the southern and northern hemisphere is actually coming together. And this is because of the use of satellite data. Since that time we are able to exploit satellite data in fact. And since the amount of satellite data is very similar on the northern and southern hemisphere, also then the skill in the prediction is very similar on the northern and the southern hemisphere. Of course, the improvement in skill is related to the fact that we get bigger computers all the time with more CPU and memory. This leads to more grid cells, better weather models, and also it leads to a better representation of the observations we can make. So that means that we can also better exploit these observations, and in particular satellites, as I said, since 2000. So to come back to the point that observations lead weather models, this is just a graph sort of depicting the data assimilation process. So if you start on the left-hand side with the green dots, which are, let's say, observations of a certain variable called x here, and you make these observations probably at different times, And then what we typically do is collect these observations in a certain time window. Here it's depicted as a 6-hour time window. And then you can make an analysis of these observations and then make a forecast with a model in time to the next observation window. And then in the next observation window you wait until it has passed and until you have observations to make a new analysis. So that means that at that point in time, in the first box you see here, that the red arrow is jumping down a little bit because that change of state in the atmospheric model is then better, more consistent with the new observations. So this, of course, can then be repeated every 6 hours, and this gives a sequence of analysis. And this sequence of analysis is also used, for instance, in reanalysis projects over very long time scales. But in practice, every day, analysis are, of course, used to start forecasts from, which is the blue line, which you see on top. And the blue line, of course, is run over a longer period at once. So that means 10 to 15 days or even longer, seasonal forecasts. But of course, as the forecast time gets longer, as I showed in the previous slide, the correspondence with the observations that will be made in the future will be smaller. So the forecast will deviate from the observations, and it also will deviate from the series of analysis. So new observations become available continuously with timeliness typically between half and 3 hours. And new model runs depend on the cutoff and the cycling time window. So usually models are typically 6 or 12 hours later only expressing the information that has been made. And that brings us to the job of a nowcaster, of course, because the nowcaster can use the freshly made observations immediately to compare it to the forecast. And before any data estimation runs have started, already see whether the forecast is correct or not in certain aspects, and therefore also change advisories based on these new observations. Well, there's a lot of new observations. So here you see the progress over the years from 1996 to 2017 in the number of instruments that has been used at ECMWF. And if the instrument is used, you can actually, the requirement is that it has a beneficial effect in the ECMF forecasting system. So all these instruments have beneficial impact. So that would mean that as a forecaster, you also could look at all these instruments to look for beneficial effects on your advisories. But that may be a bit difficult to look at all these different instruments. So you should ask again the question, what observations are really most crucial or needed to give me the information whether forecasts are correct or not. And that of course depends on the type of advice that you give. What we can say is that wind observations are most useful for mesoscale dynamics. So if we look at small scale evolution, then wind information is very important for the evolution of these small scales. So then we come to the usefulness of spectrometer data too, of course. So some idea of observations and models. So here you see Madeira in the Atlantic at the top right, and there's clouds coming from the northeast that are affected. And you see that the island is breaking the clouds because it sticks out above the clouds and is blocking the flow. And the blocked flow is creating so-called von Karman vortices. So you can see these nice swirls in the cloud pattern. That, of course, should be associated to also rotation in the winds. So that's what you can see here. So now you see ASCAT at winds from a spectrometer, 6.25 kilometer sampling. And indeed, you see that the wind is accelerated when it passes along the island, and then you see the wind is bent to the west and later on bent to the east. So you get indeed this pattern of vortices after the island with the same dimensions as you see in the cloud. So those two pictures are in fact consistent. So then we can look at the ECMF model, and you see here that the ECMF model indeed also sees the shadow of the island. It sees the wake of the island in the wind flow, but you also see that the acceleration along next to the island is a bit less, and you also that the wake is not producing these vortices. It's just a linear wake. So that's not consistent with reality. You can also look at the high resolution model. In this case it was done by Horvath et al. And it's run from the WARF model at the high resolution, so now only every so many vectors are plotted here. You now see that the acceleration next to the island is more comparable to ASCAT, but you see that in fact the vortices behind the island are totally different. So you see actually some westerly flow south of the island, where the spectrometer says that the flow is actually easterly and weak. So now you see the high resolution model is indeed adding variability, but it's not adding the features in the right place at the right time. In fact, the difference between the observations and the model is even bigger than in the ECF model, although the model has more small-scale structure. This is, of course, the problem of high-resolution modeling is that you do not always have enough observations to initialize the state of the atmosphere. So we have to deal with this. So let's go to then spectrometer or wind observations to see what they are and how they can be used. First, we can start with looking at the wind services we currently have at KNMI. So we produce 24/7 winds from a constellation of satellites. The product development has gone quite far in the last decades, so we can produce high-quality winds, and we have quality control procedures. We also, with EUMETSAT, implemented good timeliness of the European spectrometer data. They are often available even earlier than within 30 minutes. And also from other spectrometer systems, we usually get the data within a few hours, although with the current Chinese spectrometers it takes still a bit longer. Besides the services, or the service also includes service messages, so if you are interested when satellites don't work as we expect them to work, then you can ask yourself to be put on the service message list, and then you get messages when there's interruptions in the service. We also have quality assurance and monitoring of the data. And that implies that every product has a flag that says, in principle, you can trust this product or you cannot. So sometimes an instrument can fail, of course, after many years, and then usually the flag is raised in the product automatically, so that for numerical weather prediction, they can actually then ignore the corrupted data as a result of such instrument failure, for instance. Then I mentioned the software services from the Numerical Weather Prediction Satellite Application Facility, where we produce portable wind processors that everybody can, in principle, take and implement. And also in this SOF we do weather model comparison. So on this website of the NLP SOF you can find comparisons of spectrometer data with UK Met Office model data or ECF data. With these international services, there's of course lots of organizations involved, both in Europe and outside of Europe, and also many international users, such as the National Hurricane Center, Joint Typhoon Warning Center, but also a lot of numerical weather prediction centers that are using the data. You can find more information on our website, and also we have a help desk at knmi.nl, where you can get information on our services. I talked about the constellation of satellites, so the Center for Earth Observation satellites, CEOS, has several what they call virtual constellations. So it in a sense means that agencies that make certain instruments sit together and they try to make a plan of the satellite instruments that are expected. And here you see such a plan. So if you look at 2018, you in fact see the launch of ASCAT METOP-C, which indeed has been launched last year. You also see the launch of Haiyang 2B, which is a Chinese pencil beam spectrometer, which also has been launched last year. You see also a launch from SCAT on CFOSAT, also in blue, which is a Chinese-French oceanographic mission that has a spectrometer on board, and also this indeed has been launched and has now data. So we are now involved in the calibration and the validation of all these 3 new spectrometers, and we have the automatic processing already running, and these data will come available during this year. Operationally, we think after we have finished the calibration and validation together with the Chinese partners. One important thing for initialization of structures in the atmosphere is, of course, that some of the structures are in fact very fast. So if you look at, for instance, mesoscale moist convection, it usually only occurs in its extremity for a few hours, and you would not want to miss it. And you would also like to follow the evolution of those structures, and for that you would need very good time coverage. And here you see in the vertical local time of the when the satellite is descending over the equator, and that local time, of course, should you have the node for descending time, and you also have a node for ascending time. So a satellite, in principle, can pass 2 times a day. So if it has a descending node at 6 o'clock in the morning, it will also have an ascending node at 6 o'clock in the evening. So there's a 12-hour difference between ascending and descending local overpass time because of the polar satellite orbit around the Earth. So if you look at only 12 hours of the day, and the overtime pass for sun-synchronous satellites is the same every day, you can actually plan when these satellites will overpass. So you saw that in 2016 we actually had an Indian satellite at 8:45 and ASCAT data at 9:30. And in addition, we had a Chinese satellite Haiyang 2A, which has never been producing operationally data. So in fact, we only had 1 time slot a day, let's say between 8:30 and 9:30, where we have both the Indian spectrometer and the European spectrometer data, both in the morning and in the evening. So last year this has changed with the launch of new satellites. So CFOSat is flying at 7 o'clock local solar time, and Haiyang 2B at 6 o'clock local solar time. And then early next year we will have an OceanSat 3 mission, which will have local solar time, so descending node crossing time of 12 o'clock. So it means that then from next year we will actually not only have overpass times between 8:30 and 9:30, but also in fact between 6 and 7 we will have a few satellites passing over, and 6 and 7 in the morning and 6 and 7 in the evening. And also the Indian satellite would then overpass at midday and midnight. So then we have actually wind data over the ocean several times a day, which of course will change the situation quite drastically. So if you look at the WMO requirements for observation cycle requirements, it now says better than 6 hours. We had experience with earlier satellite data from OceanSat, also at 12, combined with ASCAT, and we found that they have a separation in time of 2.5 hours. So ASCAT 9:30 and OSCAT at 12. And if you do that, but that will be in the morning and in the evening. And we found that adding OSCAT data to ASCAT data in, for instance, the ECF model and the Major France model actually made more or less independent impacts on the quality of the forecasts. So we know that even if the satellites are only separated by 2.5 hours, they will already be very productive in terms of improving the forecasts. So you see that the gap remains in the morning, so between 0 and 6 there's no satellites. So we think it would be very beneficial if also there we could fill the gap, but there's no mission identified yet that could do it, so that remains to be seen. So now a little bit about a working of a spectrometer. A spectrometer is using microwave beams that are sent to the ocean surface. And here you see METOP satellite from EUMETSAT, and you see 3 arms. And these three arms constitute the antennas of ASCAT. Each arm, in fact, has two antennae, two elongated strips, which are the antenna. And they, on the ocean surface, they will show up as fan beams. So these fans on the ocean surface, as the satellite is propagating, they will constitute two swaths of data, one on the left-hand side and one on the right-hand side of the satellite. And I will show a short movie, which I hope you can also hear, to see how these 6 beams point to the ocean surface and how, as the satellite is propagating, they make swaths of wind data. Oops, that did not work. Okay. So now I have some idea of how these wind fields actually are made up by these 3 different azimuth views of the ocean. And we have to make views in different azimuth directions to get the wind direction, because the response of the ocean depends on the local wind direction. And to get an idea of the wind direction, we look in 3 different directions to get the exact direction in which the wind is flowing in between those 3 beams. So this is how we get wind direction and wind speed. So then the question is, what does a radar see? And this is a different instrument. It's actually a synthetic aperture radar, a SAR. And this is from Copernicus. It's a Sentinel-1 SAR. And you see this at the near Southampton and Portsmouth in the UK. And in fact, you see many features in this plot. So if we start on the left-hand side, then we see a box of a few kilometers size, both X and Y, and you see that it's zoomed in at the top, and there you see small waves appearing in the zoom. And this is actually what the SAR is seeing in small scales, and so from this it can actually constitute wave spectra. But this is of course not our interest. So what we see is with the spectrometer are not these waves, because at the bottom you see, also in the left-hand corner, you see 10 kilometers. So 10 kilometers is about half the size of a typical wind vector cell that we use for spectrometer wind data processing. So the green circle near the middle is more or less the size of a wind vector cell. So this green circle is not over land, it's only over sea. You see it has a black part and a gray part. It means the winds are actually quite, when it's black, the winds are very calm. And there's no microwave radiation coming back to the satellite, so it remains black. When the wind is small, then there's some roughness on the ocean, and that roughness is then causing some backscattering to the satellite antenna, and this is something that the SAR is then measuring, and then you see the gray part. So winds here will be very low, only a few meters per second. And with the spectrometer will see the average of the black and the gray, and say that the wind is small. You also see other features, like fronts. You see also a black line, which is actually an oil slick. You see ship wakes appearing, and also you see in fact the ships. You see some small white dots. Of course, if one of these white dots is also appearing in the green circle, so it means that it would be seen as contributing to the wind, but you see that it is a very small contribution in this area. So in fact, spectrometers are not so sensitive to ships. Only when there's, like say, 100 ships in a footprint, then the quality control may be active, or we may see a distortion. So it's very important to understand that spectrometer footprints are about 20 kilometers in diameter, And all these small-scale ocean features that you see in the SAR are then integrated to give one measurement of the wind factor locally. You also see that, in fact, land is bright. So we cannot move our footprints over land, because then we would get a lot of contamination of the wind by the land signal. And of course we do not want this. So that means that we may have to make sure that all the footprints that we use for wind processing will be over water. And this is in fact what we do in the coastal products. So you see modulation in shallow water, certainly at low winds, but this will be generally blurred in the spectrometer data. You still get a reliable low wind from the spectrometer. This is another picture, and the nice thing in this picture is that on the left-hand side you actually see a windmill park, and of course windmills are increasing a lot. And you see that you can see the some of the individual windmills as dots, and what you certainly see is the wake. And in fact, if you look at the scale here, so 25 kilometers is a white and a black bar. You see that even in a footprint of 25 kilometers, you could probably get an imprint of the wake of this total wind park with some hundreds of windmills. So it means that spectrometers will automatically adapt, of course, to the presence of the windmill parks. But models not always have. So this is also interesting for development to note. So I mentioned this constellation of satellites, so we start to get a lot of instruments, and of course the question is, how can we combine all these different instruments for you to have a good view. So on the right hand side you see now all our products. You see there's too many products to click on to get an overview, and that's why we made this tile viewer. And in the tile viewer we plot all the data on one map, and then you can click on the map in your local area, and then you get that particular tile of winds, and you get all the winds, all the satellite instruments that passed that tile over the last 24 hours, and you get an image of the wind as it changed over time. So this is an example of how these winds look like. So here you see something in the Denmark Strait. You see here reddish flags. These reddish flags are the spectrometer wind field. Constitute spectrometer wind field, but you also see green flags. So the green flags are the winds computed from the ECMF forecast. So they are interpolated to the spectrometer track, and they also in the same representation. We call them stress equivalent winds. And you see there are some differences in the wind direction and the wind speed, and of course these differences may cause you to give some different advice in certain areas. On the right hand side you see another representation in arrows. Again, the colors are the same, so you see the different spectrometer winds in different colors, from blue to red. In this case it's Mangkhut hurricane. And you again see the ECMF winds as green arrows. And again you can see that in some areas there are differences between the observations and the model, which may be useful to know if you are making forecasts. So as a nowcaster you have access to the numeric weather picture forecasts, and advisories are based on this usually, and therefore differences between the green, the forecasts, and the reddish arrows, the new observations, may imply a revision of your advisories. And that's why spectrometer data can be very useful to follow in near real time. Now we have a look at different spectrometers. This is a SCATSAT. It's a rotating pencil beam spectrometer. It has a 1800 kilometer wide swath. It has a large coverage. But you see that in this case, which was a quite severe Mediterranean storm, you see many black arrows. These black arrows are arrows that are rejected by our quality control. Well, some of those are probably still okay, so we are continuously trying to improve our quality control to give you a better view on what we think is suspect and what we think is good. You also see that some of the reddish arrows differ from the green as before, so giving you some information of where the forecast at that time was correct and where it's not. You also see that the winds are not very close to the coast, and this is because of the particular processing concept. For these pencil beam spectrometers, we don't have the information to process them closer to the coast, so that's why we stay away from the coast. Another last feature is that the wind fields actually looks quite smooth, and this is because of the noise in this type of spectrometer measurements. We have to apply some special algorithm to get a unique winds. And that makes that the wind field looks a bit smoother than the wind field from ASCAT. So this is the wind field from ASCAT. And the ASCAT winds, they show more detail. But the disadvantage is, you see on the left-hand side at the top and the right-hand side at the bottom, that there is no winds. And this has to do with the narrow swath of ASCAT on one side, which is only 550 kilometers. So you have now two 550 kilometer swaths instead of one 1800 kilometer swath. The advantage of ASCAT is that it's working in C-band. It's a larger wavelength than the pencil beam spectrometers, which work in Ku band. And that means it's less sensitive to rain. So you see now there's almost no points that are rejected because of rain, no black arrows. Also, we have more information in the system of where the footprint is, so we can process closer to the coast. And we don't have to do any spatial filtering, so that means that we can keep more mesoscale detail. We can keep the original detail measured by the instrument, so more detail than in SCATSAT. We have ASCAT A, but we also have ASCAT B, and you can combine them. And of course, if you combine A and B, you get more coverage. So at the moment we have ASCAT A, B, and C. Still we have low rejection. We are close to the coast. And now with ASCAT A, B, and C, we have the same coverage as one SCATSAT or Hyang 2B pencil beam spectrometer at Ku band. But we still have therefore some advantages in terms of data rejection and closeness to the coast. Spectrometer processing works in the following way. We need the input values of backscatter. So we measure how much of the radar beam that is emitted to the ocean is backscattered to the antenna. And these backscatter measurements are then normalized and they are called sigma naught. So we have input sigma naught values. We have a pre-processing step where we check the quality of the inputs, whether it's according to expectation. And then we have values for each of the different beams that contribute to a local wind vector cell. So for ASCAT we have 3 beams, forward, mid and aft beam, as I showed in the movie. And then we process them together in a wind inversion step. And then we get more than one solution. For ASCAT we get usually 2 solutions. And then we have a step which is called ambiguity removal, where we use where we actually make a 2D VAR analysis of the spectrometer data and the ECMF forecast. And then we use that analysis to pick one of the 2 solutions. And for ASCAT this is sufficient to get a unique wind field in most of the cases. So then you get a unique wind field from the spectrometer. But for these pencil beam spectrometers, we actually have to look at more than 2 solutions, and therefore you also get a spatial filtering effect, as I mentioned. Then we have buoy verification. We do this every month, and you can find these statistics on the website, and you see that in general the spectrometer winds and the buoy winds, they look very much like each other. Then we verify the quality of the buoy winds and the spectrometer winds and the ECMF winds as a function of, we compare them with each other in a process called triple collocation. And then you see that if you look at the top here, that the ASCAT winds have errors in the wind components of typically 0.7 or 8.8 meter per second. You see that the buoy errors are in fact larger, and this has to do with the fact that here we measure the error of the wind on a 25 kilometer scale, the footprint scale, wind vector cell scale, and the buoy winds are a point measurement somewhere in this area, and that's why you get this variance in the buoy error. The ECF error on the spectrometer scale is again bigger than the buoy data because the ECF model is smoother, so it does not represent the 25 kilometer scale that is seen by the spectrometer. You miss some mesoscale details, such as from moist convection. Okay. So I mentioned already the quality control. Here you see another example for KU band quality control, where you see that some areas with rain are in fact flagged, but most of the areas remain green, so you still can depict the structure of the storm in this case. So for KU band systems, on average we reject about 5% of the data, but we have some indications that we can make this percentage lower, and we are doing some further research on that. If you compare that to ASCAT, for ASCAT we only reject 0.5% of cases. And these are generally cases with a lot of wind variability, so these are near fronts or low pressure systems. But it's a very small, it's less, only 0.5% of data. And then if we look at those data that we reject, you see here from the black box is the box where we do where we have the thresholds for data rejection for ASCAT. If you then plot the winds in this box, that are collocated with buoys, then you get the black points. But then if we do a buoy time averaging to be equivalent to the 25 kilometer footprint, then we see that the fit is improving. So then we get a standard deviation of those bad winds, only the 0.5% that are worst, but there's still 1.8 meter per second. So even the ASCAT bad winds are in fact not so bad. What are the reasons for these unrepresentative data? Well, one reason is moist convection. So I mentioned ASCAT A and B that are flying at 9:30 in the morning, almost in the same orbit. When we first got this data, we looked of course at the data when they were overlapping, and here you see in blue data that was measured at 10:40. And in red, data measured at 11:30. So there's 50-minute difference between the two measurements. You see that most of the arrows look actually very similar, but there are areas where you see the cloud image is white, so there's intense clouds and moist convection. You see actually that the winds change, and this is because of the downburst of wind, because of rain. That is causing such big changes in moist convection areas. So for spectrometer winds, you can say that many more will appear soon. We have HyYang2B, CFOSat, ASCAT-C, we'll get OceanSat and WindRat in 2020, so we'll get many more of these data. They represent a mean wind vector cell wind, and they are provided as stress equivalent neutral winds, and can be treated for nowcasting purposes as normal winds. They verify well with numerical weather picture models and buoys. Also the spectra, they look close to what we expect for 3D turbulence, for scales down to 25 kilometers. And also in spatial plots you see these small scale features, and you see that they align with moist convection, for instance, and other meteorological phenomena. We screen them for land, sea ice and rain. We still are working on calibration, in fact having in situ reference for winds above 30 meters per second. And also for some systems we are still working on improving the ambiguity removal for the systems. So now let's look at model winds. Of course, the global circulation models are improving all the time, as I mentioned. We have a lot of boxes, and for these boxes we need initial data to initialize the state variables in these boxes. And of course we could use winds for that. And we start then by looking at the differences between the spectrometer winds and the numerical weather prediction model winds. At the top you see a map which is a collection of about 9 months of differences between ASCAT and ECMF. And then at the bottom you see the same plot for the same points, but then a difference between rapid scat and ECMF. So rapid scat was a pencil beam KU band scatometer, and ASCAT is a fan beam C band scatometer. So in principle they are different instruments. But if you look at the differences over 9 months between these two systems and ECMF, you see that the differences are actually look very similar. And these similar patterns, they appear not only after 9 months, but they actually appear every day. And this is due to convection, to parameterization, to ocean currents, and to effects that are actually very persistent over time. So you very clearly see the ITC set, and you see the trades, you see the Gulf Stream areas, etc. So it's in fact important to know these systematic effects and try to correct for them if you use the winds. This is again wind speed for ASCAT, the differences with ECMF, and normally ASCAT minus ECMF. You see it now also for different seasons. So on the top you see it for a whole year, and then at the bottom you see December, January, February, March, April, May, June, July, August, September, October, November. The scale is between -2 and +2 meters per second. So you see that some of these features are modulated by season, but they actually remain present for most of the year. Another important aspect of comparing models and observations has to do with the drag formulation in the model. Particularly for extreme winds, the drag is quite important to specify, because if the drag is wrong, the winds may be too high or too low in the model. And then of course the scatometer data should be calibrated such that they can tell whether the model drag is alright or not, and we are working on this. I mentioned parameterization errors, so there's a lack of cross isobar flow in numerical weather prediction, and you can find several references on those from Brown and Sandhu. And you can see it as a difference between when the wind is affecting warm air to colder water, or the other way around, cold air over warm water, and particularly when there is advection of warm air over colder water. You see a large red or blue, depending on the hemisphere, errors, which are typically up to 10 degrees. So you see on average over the northern hemisphere 6 degrees, southern hemisphere 5.7, over the whole hemisphere quite large errors in the case of warm advection. For other models we get similar problems, and it has to do with the closure of the stable boundary layer. So it's a parameterization effect. It's difficult to cure this effect because it affects also the forecast scale, because a different turning of the winds could help fill in the low pressure systems and therefore destroy the forecasts. Here's a plot, it's a spectrum. So here you see on the horizontal scale the wave number. If the wave number is small, the scales are large. If the wave number is large, the scales are small. So I plotted a line of 100 kilometers in here. That's the wavelength. And you see, if you compare the scatometer solid lines or dash lines with the ECMF dash lines at the bottom, you see that there's typically more than an order of magnitude difference in the energy density, which means that in fact on those scales the ECMF model is lacking scales that are seen in the scatometer data, down to 25 kilometers as I mentioned. So if you are looking for mesoscale structures, watch for scatometer winds over sea. Of course you could create smaller scales by doing downscaling of a global model. This is done here. And then they verified this downscaling by the high resolution structures generated by the high resolution model, verified that with the QuickScat scatometer data. And what you see is that downscaling actually can be quite beneficial near coastlines. That's where you see the red color, which means in those cases the downscaling has led to an improvement of the wind, or at least a better comparison to QuickScat. But over the open ocean, it leads to the degradation of the winds. So if you do run a higher resolution model, you get lower quality winds because the model is actually generating noise. This is because there is too little forcing over the open ocean to predict what the phase of all these small-scale disturbances is. So it will create small-scale disturbances, but they will be at the wrong place and the wrong time, and therefore if you do RMS verification, you will find that the wind skill is lower in a deterministic sense. So if you look at NLP model winds, they are initialized from observation data estimation system. They are improving the forecaster's reference. New observations are not used with the 12-hour lag. So a lot can happen, of course, in 12 hours on the mesoscale. So if you then have new timely observations, you could, of course, then check and amend warnings, either current ones or the ones that you are planning to issue for the future. NLP model winds also lack true mesoscale variability in the open ocean, since this is poorly observed in 4D and there's not deterministic forcing that can give you this variability in the open ocean. Model winds are also not so good in the tropics or elsewhere near moist convection, such as polar lows. And also they have some systematic wind biases, for instance in stable air due to ocean currents or the diurnal cycle. So now we can do the last bit, which is on mesoscale forecasting, and just give some examples. The first point is quite important. It's about spatial representation. So we estimate area mean wind vector cell winds using empirical geophysical model functions. But the important thing is that we do this over 25-kilometer areas. And the plot here is actually showing a wind time series, which is measured at the buoy. And then it's assumed that the mean wind is being affected along the buoy. The variability is affected by the mean wind along the buoy. So you can actually change the time scale into a space scale in distance. So that's how you get a buoy series as a function of distance. And then you can average it over 25 kilometers to simulate the ASCAT footprint. So then you get the green line. And you see that the green line has lower extremes than the blue line because it's actually smoothing the extremes. So this is what you expect. And then we also have the red line. The red line is actually representing the ECMF smoothness. And again, you see that the ECMF extremes are lower than the spectrometer extremes and also lower than the buoy extremes. So the spatial representation is actually quite important to get ideas about the, for instance, 10-minute sustained winds or 1-minute sustained winds. So you expect them to be less extreme. So you need some guidance to go from these model winds and spectrometer winds to 1-minute sustained winds or 10-minute sustained winds. So this is typically what is called the gustiness factor that has to be taken into account. So all these different systems have different probability density functions, different climatological values too. So if you look at spectrometer data are very much used in tropical cyclone forecasting and also being beneficial for numerical weather prediction, for instance the ECF model. Of course, at high winds, it's quite nice to get such a good coverage of spectrometer winds. Particularly NOAA has a lot of experience in better warning systems using spectrometer data. In the Netherlands, I looked at this case, which was a storm surge in the north of the Netherlands, where it was very clear that the blue and the green flags, in this case, underpredicted the storm surge by half a meter. One because the direction was wrong, and the other one because the speed was wrong. And if you looked at the QuickSCAT data a few hours in advance, then you could see actually these errors, and you would be able to give a better depiction of the storm surge in this case. So this is a plot showing our HIRLA model and in blue and spectrometer data in red, and you clearly see that there's a difference in the development phase of this podal disturbance that is moving towards the Netherlands. And of course, spectrometer data are very nice to pinpoint such phase differences in development of systems, and of course that has implications for warnings later on. This is a case of moist convection near Lake Victoria, where you see when I was giving a training course in South Africa on 8 December 2016, we looked at cases over Lake Victoria. You see HCAT-A. In green you see actually very little wind in ECBF, but HCAT is showing 25 knots because of local downburst, because of clearly moist convection, as you can see in the cloud image. So 50 minutes later we have HCAT-B, also showing the same picture, but now the HCAT winds have changed actually quite dramatically because the convection has of course evolved in 50 minutes. So you see that the wind has changed quite a bit too, even in this time frame of 50 minutes. Last 2 points I want to say is that spectrometers also can give information about sea ice and sea ice climatology, and also about soil moisture. So we make a soil water index. And from this soil water index you can also get integrated rain in semi-arid areas, and also some information about vegetation. So this information is also being exploited for spectrometer data. I put in some slides for further references that I will put online after this talk, and also some training information and ocean references. And that brings me to the end of this talk, and I would like to thank everybody for listening to this. Thank you.